We share
theoretical and empirical reviews.
It is all about learning research facts and sharing with others.
Subscribe to our channel. Title of the paper: Heat transport of magnetized Newtonian nanoliquids in an annular space between porous vertical cylinders with discrete heat source. Authors of the paper: Details of the paper. Before we present the theoretical review, let us consider a preliminary introduction.
Sherwood number proportional to mass transfer rate, velocity, temperature distribution, concentration, friction coefficients, and Nusselt number are some of the properties of either static or flowing fluids.
Nusselt number is the ratio of convective to conductive heat transfer at a boundary in a fluid. Nusselt number is also known as the ratio of the thermal energy convected to the fluid to the thermal energy conducted within the fluid. Nusselt number is equal to the dimensionless temperature gradient at the surface multiplied by -1 associated with the direction of heat, and it provides a measure of the convection heat transfer occurring at the surface. It is worth remarking that the Nusselt number is proportional to the heat transfer rate from the wall into the fluid. However, nothing is known either the proportionality is direct or inverse.
Considering classical Socrates and Blasius flows, it would be discovered that increasing Prandtl number corresponds to a growth in the Nusselt number.
Table 2 presented by some scholars in the year 2020 shows that the Nusselt number increases with the Prandtl number at the rate of 0.144395.
So, if it is accepted that increasing Prandtl number implies an increase in the momentum diffusivity at a fixed thermal diffusivity, then the proportionality is inverse because lower values of Nusselt number are seen at smaller values of Prandtl for a lesser viscous fluid. Besides, heat energy is expected to transfer very fast in a lesser viscous fluid.
Based on this, it may be realistic to accept the fact that the Nusselt number is inversely proportional to the heat transfer rate across the fluid.
A Nusselt number of nu equals 1 for a fluid layer represents heat transfer across the layer by pure conduction.
A large Nusselt number implies that convection occurs as the wall moves and heat flux is more efficient.
According to Ken Licker, 2014, the Nusselt number in the fully developed laminar flow is a constant property that depends on the channel geometry and the wall heat transfer boundary condition.
Consequently, convective heating, predefined heat flux, predefined surface temperature, and thermal stratification at the wall are some of the factors that could strongly influence Nusselt number.
Analysis of thermally fully developed flow of nanofluids inside a vertical annulus by Ganji and Malvandi, 2016, shows that increases slip parameter intensify the Nusselt number and consequently, valid to remark that nanofluids can transfer heat energy more efficiently in a slip condition than in a non-slip condition.
In other words, the slip condition enhances heat transfer. More so, as buoyancy-related parameter, Grashof number, increases, the Nusselt number increases in such a way that efficiency, i.e. ratio of the heat transfer rate to the pressure coefficient, diminishes.
In a study on the significance of dual stretching on the dynamics of various hybrid nanofluids by some scholars in the year 2020, the rate of increase in the Nusselt number due to increasing velocity ratio is 1.34604111 when suction is small and one of the nanoparticles that form the hybrid nanofluid is titanium dioxide.
Also, the rate of increase in the Nusselt number due to the higher velocity ratio is 1.32366972 when suction is also small but one of the nanoparticles is silver.
In a study on the dynamics of titanium nanofluids of different base fluids, i.e. ethylene glycol, engine oil, and water, in a cylindrical annulus with discrete heat source by Mebarek-Oudina, 2018, it was discovered that local Nusselt of a source of length equals 0.4 is minimum when the Rayleigh number is small.
Optimal local Nusselt is ascertained when the Rayleigh number is sufficiently large. More so, the value of the local Nusselt number increases with increasing nanoparticle volume fraction for all base fluids.
It was also concluded that the average Nusselt number depends on the change of the base fluid.
Analysis of molybdenum disulfide nanofluid in a channel with different nanoparticle shapes by some scholars in the year 2019 reveals that spherical nanoparticles boosted the local Nusselt number more than the other considered nanoparticles. Next, we shall now present the theoretical review.
Dynamics of 4 nanofluids through a porous medium situated in the cylindrical annulus with radii subject to Lorentz force was examined using the Darcy-Brinkmann model for the porosity. The 4 nanofluids are water-based nanofluid made up of
A. Copper nanoparticles, B. Alumina nanoparticles, C. Silver, and D. Titanium dioxide, also called titania.
the dimensional governing equations suitable to explore the increasing size of the heater, Hartmann number, and volume fraction of nanoparticles were presented, solved, and explored. Next is to present the empirical review.
The analysis presented shows that 1. The average Nusselt number increases with a higher volume of nanoparticles in the base fluid. A higher Nusselt number was seen in the dynamics of water silver nanofluid but lower in the dynamics of water titania.
2. The same average Nusselt number declines due to an increase in the size of the heater.
3. The average Nusselt number was found to be maxima at all the increasing size of the heater. However, the same property is minima and linear as the size of the heater increases. Acknowledgements.
Special thanks to all the editors and reviewers of International Communications in Heat and Mass Transfer, Elsevier Publishing. We share appreciates the contribution of the authors to the body of knowledge.